Hi everyone. So I wanted to do some lectures where I kind of go through my thoughts on these various elements, and then you can watch these hopefully at high speeds and get the kind of big overview, and then hopefully, yeah, if you watch them on your own time, we can kind of get our collective understanding to a common location, and then I think our group meetings will be more productive. So as the first lecture, I want to talk about learning and just why we can move to this augmented space and how that kind of solves most of the problems with learning that at least I've had in thinking about learning and control. Right. So the system I've been imagining is an electron. Okay, wait, an electron, and it's entering this field. Right, so over here we have, a magnetic field H, and we don't know which direction it points. Right, or sorry, let's call it an electric field. To simplify things, yeah. So this thing can point up or down. We don't know this parameter, right? So this thing is coming through. It has a position and velocity. Let's call it q and q prime, q and q dot, and it's going to enter this field. And depending on the velocity, it's going to travel like this, or depending on the field, it's going to travel in one of these directions, right? So kind of the annoying thing about thinking about this problem is that the system is not really Markovian, right? So the dynamics, if you look at this later point here along this trajectory, right, the propagator for this depends on what we've seen in the past, right? It depends on what our belief about the electric field is. So it makes a lot more sense to take this and kind of augment the space with another dimension, right? So that the electric field is on the x-axis and the paths are kind of in this three-dimensional box, right? And then we have just this kind of fan of paths where depending on the electric field, you actually identify a different path. And for this joint system, this augmented space, so this is E, this is X, yeah, so this is, right, for this augmented space, you actually recover the Markovian property. And that's kind of the key idea to make all the control theory make sense. So, yeah, so that kind of motivates defining this, defining our system states to be this cross product of the system state and the parameters of the system, right? And once you do that, it really just reduces to this partially observable Markov process. And so initially, you don't actually know what theta is, right? So really, this is partially observable in the sense that you have these x, the states, but you can only observe s. So the observations are really this projection from the state to the subspace of x. So these are your observations, right? So this is kind of the standard picture for a partially observable Markov process where you have these observations and these underlying states. And we don't really get any information about the electric field until we cross into this region where the electric field is present. So it's only at this point, say this one x3, where we actually see, okay, theta is, or the electric field, our observations tell us that the electric field is, E is positive. And then we actually know more about the system, and we learn something about the propagator that's governing these underlying transitions. So the electric field is constant in this picture, but we're trying to learn what the total propagator for the system is. So let's call the propagator between x1 and x2. I call this little k. X2 given x1, right? It's just basically that the position is the change in position is equal to the change in velocity, or is equal to the velocity. So I mean, my notation is kind of sucky, but this is the idea. And the velocity is the acceleration of the velocity is 0, right? Because we're outside the electric field. But then the propagator for x2, x3 given x2, right now we're inside the electric field. So q dot equals v and q v dot equals qv over m. So now, based on how we see the acceleration change, we actually get information about E, right? So k depends implicitly, it's this function on state, but also on theta, right? And it actually has kind of a likelihood value for E. So depending on how you see the state change, you update your prior for the possible electric field configurations, right? So your prior is on theta. This is equal to, say, for instance, a Gaussian distribution maybe about 0, but it doesn't really matter. Right, so we have some understanding of how these electric fields could be distributed based on our setup, and right. So when you see what happens when the particle enters the electric field, so this is the prior at time 0. So at time 3, when you've entered the electric field, this becomes a delta function at v dot the observed acceleration times m over q. Right. So there's this posterior update that depends on the likelihood that's kind of encoded in this propagator. So what we're really interested in, if we're thinking about applying control, is the state of our knowledge of the system. And so we have to understand how our knowledge of the system changes based on our understanding of the dynamics and the observations we see. The control at time t has to be dependent only on the observations we've seen up until that time. And we can encode the information in all these observations in the posterior distribution, right? So this is equivalent to oops, too big. This is equivalent to the posterior, right? That kind of carries all the information about all the observations that's relevant to our current understanding of the state, right? So this is a way of encoding all previous observations. It's the sufficient statistics for any decision we would like to make about the system. Oops. Right, and so since this is the structure of our control, this thing is really, in a standard control sense, the state that our policy depends on, right? So all of our states are really just posteriors on this kind of this space here, which is, just to remind you, S and theta. So X, right, so it's really a standard control problem, but, X has some interesting dynamics. This big capital X has some interesting dynamics. And so now let's just talk quickly about what those dynamics are. So it's a posterior, right? So you can think of X of t as represented by kind of a point cloud. So this is the state space. Oops. This is the state space, right? And you have this cloud of points. And for each of these points, because you know what theta is, you actually know the propagator, right? So as you evolve in time, these states kind of move stochastically according to the propagator, right? So this is governed by little k. X of t plus 1 given x of t. Running out of room. I wish I could extend things in that direction. So little k governs the dynamics of all these points. And then there's this other thing that can happen, which is that you can observe something. And every time an observation happens, right? So given an observation at a particular time point, what happens is you take this cloud of points and you say, okay, actually, only these are compatible with the observation. So these points get killed off. And these points can kind of reproduce according to essentially the likelihood. So there's a likelihood on x given theta, or given the observations. Right, and it's the combination of these two processes, the internal diffusion of these points and the application of this likelihood, that really describes how our full state, our knowledge state, is evolving through time. So that's kind of this full propagator, capital K on capital X. It's this composition of two processes. It's equal to this kind of convolution on the this deterministic convolution on the posterior, right? So you have let's call it little k on and this is convolved with bar pi x of t. And then this is also multiplied by the likelihood x of t plus 1 given the observation t plus 1. Right, and normalized. So this is kind of actually a nonlinear operation. So it's just saying, to move your whole knowledge state forward in time, you have to apply this propagator at each point, moving each point along its kind of internal known dynamical trajectory. And then you update your knowledge about the ensemble based on the observations you see. And I actually want to emphasize that the dynamics of capital X, the dynamics of our posterior, are fully Markovian. So these observations, the distribution of O of t is given by the likelihood for t. So let's call it Q of O of t given x, just averaged over the posterior for x. So right, so this is kind of sorry, not equals, but is distributed from this distribution. So that means we can generate the x of t plus 1, generate our new posteriors by this kind of two-step process. So first, you take your point cloud. Well, I guess it's more than two steps. You take your point cloud, you evolve each point according to possibly stochastic propagator k, little k of x, t plus 1, given x of t. And then you can draw, take one of these guys from its new location. So you draw randomly from your point cloud and say, okay, that's my putative x naught, the true value of the system right now. And we can use that to generate samples. So an O of t is drawn from the distribution. And then you can update your system based on the likelihood for O of t. So right, so O of t was drawn here, so the likelihood is probably kind of centered around here. And so you kill off these trajectories based on the L of. So yeah, it's I guess a three-step process. And then what you left up with is, this ensemble of configurations is your new x of t plus 1. So that's kind of the sequence. It's perfectly possible to simulate forward in time from this system, and it's perfectly Markovian. And so that means the laws of control theory are applicable to this posterior space, right? So that's kind of maybe the starting point for this analysis.